Hi, in this video, we're going to take a look at random forests. All right, so random forests are by far my favorite model to use for supervised learning. So I've had a ton of success using random forest. They are easier on the data prep side. They are accurate. It usually takes a lot of work to do better than a random forest model. And so I'm really biased, but I feel like random forest is like the go-to for any supervised learning project that you're working on. And so I strongly recommend that you give this a try on all of your projects. If you've got different models that you can go for. Now it is a little bit black box-ish, but we still get like some good information about which variables are important from random forest. All right, so how does a random forest work? Well, what we're going to do is we're going to build a decision tree, and then we're going to build another one, and then we're going to build another one, then we're going to build another one, and then we're going to build another one, and we're going to have a collection of decision trees, which we'll go ahead and call a forest. All right, so that's a forest of decision trees. Now, what I just talked about, there's no randomness in those decision trees. Where do we get our random forest? Well, what we're going to do is we're going to randomly select a subset of our predictor variables. But wait, there's more. We're going to take a random subset of our rows of data. And in fact, we'll go ahead and bootstrap that. And so what we're going to end up having is that we've got a random sample of our rows of data. We have random selection of our columns of data where you're only using a subset. And then we're going to build that decision tree. All right. And so then I got one decision tree. I'm going to redo that process, doing the bootstrap, doing the variable selection, I get another tree. And then I redo that process of random sample on the rows and random selection on the columns, got another decision tree. And I keep on doing that, 50 to 200 times ish. And then how am I going to combine them all together? Well, there's different ways to go about it. One way would be to take the average of predicted values. So each tree gives a predicted value of the target variable. Well, for the forest as a whole, how do we combine all of those individual predictions? Well, we could average them if I have a regression target, or I could go ahead and do like a voting system of the one that's most frequent for situations like for categorical classification. All right, so random forests are powerful and they're popular for supervised learning. They constitute an ensemble learning techniques, specifically ensemble of decision trees, which means they combine the predictions of several base estimators to improve the overall generalizability and robustness of the prediction. And so when I say ensemble, either we're going to be doing like that voting method, or we're going to be going and doing that regression averaging. The underlying idea of a random forest is simple. Instead of relying on a single decision tree or a single model, we build a whole bunch of models and we let them vote for which one's most popular for classification, or we average them for regression problems. By doing so, random forest is able to capture complex patterns in the data, and they're less prone to overfitting than individual decision trees. All right, so let's go ahead and get things started. I'm going to set up my workspace. So I suppress the number of digits to be printed. Try to stick with non-scientific notation as much as possible, and suppress warnings that I don't really care about. Here I'm making sure that my workspace is clear, and I'm going to be using piping, so I go ahead and pull this in. All right, so why would we use a random forest? Well, they're accurate compared to other supervised learning techniques. They can handle large data sets, and they balance that bias variance trade-off very well. Also, they're versatile. They can be used for regression and classification tasks. And so a lot of times when I'm working on a project, I'll put random forest as kind of like, all right, you got to beat this for me to consider using a particular model. So if I do like support vector machines, or I do logistic regression or k-nearest neighbor, something like that, I say, hey, here's my random forest. You got to at least beat random forest for me to use you instead of random forest. I'm very biased. I lean towards random forest. And also, one thing that I like about random forest compared to boosting is that, and we'll talk about boosting in an upcoming video, is that random forest, each individual tree can be used as a model by itself. Each tree is individually useful on its own as a predictive model. This is not true in boosting. When we're doing something like extreme gradient boosting, add boost, or stochastic gradient boosting, trees after tree number one depend on the previous trees to be used. And so that, to me, that makes it harder to interpret what's going on, because I can't like just grab a single tree and interpret it. I have to interpret all the trees prior. All right, so remember that when we do a random forest, we're going to be doing decision trees. And these are the foundational building blocks of random forests. And decision trees split the data into subsets using some form of decision. In a previous video, I talked about decision trees, how those are built up. I use the rpart package for that. And each decision is based on the value of one input variable, and this results in a tree-like model of decision. So we split left or right, yes or no, on or off on our decision tree. All right, so let's go ahead and take a look at the house price regression data for this. So I'm going to go ahead and load my data here, and I'm going to filter my data to just the training sets. And now when I do that, so there's a test set and there's a training set for this. Well, this is a Kaggle competition data set, and that test set is for the competition, not for my personal use. I don't know the true values on the test set. So I'm getting rid of the test set data. And on this one, I'm defining a new train test partition on there. And in just previous modeling I've done, I've decided that these predictor variables are the ones I want to focus on the most. All right, so under the hood. So first and foremost, random forests use bootstrapping. That means that if I had 1,000 rows of data, I'm going to go through and I'm going to randomly select with replacement 1,000 rows of data. All right, so we're sampling with replacement. When I do that, some of my observations are going to be left out. We're going to call those the out of bag observations. And so also, when we do sampling with replacement, some observations will appear more, like far more than others. And so it's possible that one row is going to be in my bootstrap sample 10 times, another one 12 times, another twice, another 7 times. And so this randomness actually improves the model overall, because it generates some variability in what I get for my actual predicted values. And I can actually use this to get a better idea of the distribution on the target variable that I'm going after. Now, when we do a decision tree, what's going to happen is that each split, the best split that can be obtained using the rows of data that I selected and the subset of predictor variables that were randomly picked, is how we set up that decision of left and right. So here, remember that the random subset of features is chosen for this. And so when it finds the best split of those features, it's not the best possible split of the entire data set. It's the best possible split of the bootstrapped observations and the subset of selected variables. And so by doing this, we get a lot more diversity in what's going on for our predictions than we would if I had a single decision tree. And so that we could actually use this for like hypothesis testing, and we could get like more information about what's going on by using the distribution we get from this randomization aspect. All right, so bootstrap our sample of size n. So whenever we bootstrap, if I have 1,000 original observations, I sample with replacement 1,000 of those observations. Remember that some of them will be selected more than once, some won't be selected at all. The ones that are not selected are the out of bag observations. And so then, we're going to build decision trees, typically 50 to 200. And then, we're going to use those to combine to form my tree. or to form the forest. And then when I make a prediction, we're going to do like majority voting if it's a classification problem, or we're going to do averaging of the average of the predicted value if it's a regression problem. All right, now there are two major packages in R for this: random forest and ranger. My experience is that random forest and ranger are about equally useful in terms of accuracy. They're about equally accurate. Now, for the purpose of a hypothesis testing, for the problems I've been working on when I've had such problems to answer at work, random forest is just better supported for like the types of questions that statisticians would be going into to get a deeper perspective of what's going on. Now, for predictions, they're about equal to each other, but Ranger is a lot faster than the random forest package. Ranger is blazing fast. I like it. I love it. I want more of it. And so that's the one that I typically use most of the time for work. Honestly, when I've built models and I'm using the same data, it's about a 50-50 split if random forest or ranger is going to be the more accurate of the two. Well, they're about, and they're honestly not that far apart from each other in terms of accuracy, but ranger is so much faster that it helps me get through my project quicker. I prefer ranger. But both are good, both are excellent. Random forest is the default method in the carrot package, which should show you it is ultra useful on its own. All right, so here you'll notice that I've got default settings for my random forest using the Ranger package. We set up our formula and our data. And so here I'm just putting it, I'm only giving the target and predictor variables in here. And you'll notice I'm using the period to say all other columns are in this formula in the R notation. And so we can see that's a regression target variable. We have 500 trees, which is a good number. Scikit-learn, I think the default is 100 for scikit-learn. Typically, there I used 200 for what I'm doing. Actually, no, I'm remembering stochastic gradient boosting. I can't remember what the default is for scikit-learn. But here's my sample size. And remember that is the training sample after I kicked out the test set from Kaggle and after I partitioned my data into train tests. Here's the number of independent variables total. This is the number that were randomly selected on each tree. Target node size, minimum observations inside each leaf. And here I did not calculate variable importance. If I want variable importance, I have to actually specify it in the parameters up here. I have default split rule. So here, this is going to be like trying to reduce the variance, similar to how like a NOVA reduces variance, and by trying to account for the variability in the target variable. Now, remember, I did that bootstrap business, and I had data that was not in the training data for this. Well, what the Ranger package does, it takes all of that excluded data from the bootstrap sample, and it goes ahead and it calculates accuracy on that. This is very nice. And so if I'm short on data, I'm having trouble getting a train test split because I have such little data. If I can get random forest to be reasonable, random forest actually already does in a certain sense a validation step for me. And so this is very nice. Now, my personal experience is that out of bag prediction error tends to be optimistic when compared to the validation, and validation tends to be optimistic compared to test statistics, and test statistics are optimistic compared to what actually happens down the road. So my experience is that out of bag prediction error is somewhere between your training prediction error and your validation prediction error. So keep that in mind if you're using this. This is a great option if I have some data enough to start building models, but not enough to do the train validation test partitions that I really should be doing. And here's our R squared out of bag measurements. All right. Now here, the tree info function in Ranger, we can pull any single tree we want. So here we've got 500 different trees. I could pick 1 through 500. All of them are individually able to stand on their own as a model. And because of that, this is one of the things that I really like about random forest over stochastic gradient boosting or extreme gradient boosting, is that each individual tree, it can stand on its own. And so here, we have just the rules of our tree. If I wanted to go through and work through this step by step, quite a bit. And now something about decision trees and forests. A good way to think about decision trees, random forest, and boosted forests are that this is kind of like a Goldilocks situation. Random forest goes too deep. Stochastic gradient boosting doesn't go deep enough, but adjusts for the errors, and then decision trees try to be just right. So there's a continuum there. So random forest, the trees actually go individually too deep. And if I wanted to use individual tree, I really should prune the individual tree. But what ends up happening is that when I average over all 500 trees, they end up averaging out to be a pretty good estimate. So I may actually go too deep, but it's okay because in the end, I average everything together and it works out beautifully. I need to scroll through this. All right, well, overshot that by a little bit. All right, here we go. Now, there are some parameters that we're going to need to worry about. Now, remember, our parameters and parameter tuning are nowhere near as important as my model structure, and they're nowhere near as important as the data I'm feeding in. If I have problems, parameter tuning probably isn't going to fix it. Honestly, it's just not going to fix it. If my model isn't good enough, I need to go back into the data to be able to get my model to fit. But here are the hyperparameters that we typically worry about to kind of fine tune. So remember, parameter tuning is exactly that. It's tuning. Like when we tune up our car isn't far from performing well, but it's not optimal. This isn't a whole engine overhaul. Parameter tuning is a slight tweaking to get better performance. So the first thing is going to be the number of trees. I've seen I think 50 is what Enterprise Miner uses. The default for Ranger Random Forest is 500. mtry is the number of variables used in our model and for individual trees. Typically, I've seen 70% or square root of the number of predictor variables as reasonable choices. Now, another one what we can choose is maximum depth to try and prevent our trees from going too deep. I typically don't mess with this. And we could also do minimum node size. I've used this one in the past so that just to make sure that all my averages are at least somewhat sensible. So I didn't have overfitting on individual trees too severely. Typically, random forest individual trees are overfitted because they're too deep, but they average out to be all right. And so here I'm just running through an example where I just tried several different values. And on these values, I use the caret package and the train function to find what would be good parameters to use. And so here, we can see have a 0.87 for our R squared out of the bag. What did we have before? Oh, it's too high up. I'm not going to look at it. All right, so now there's some advantages and disadvantages of random forest. So random forest does a good job with large data sets. It provides a variable importance score so we can see what's important in our model. And honestly, it's less prone to overfitting because of that averaging. But there are some major disadvantages. It's very black box-ish. Compared to like linear regression, generalized linear models, I have no idea why something is getting picked the way it is. These can be computationally intensive, especially if I have a large number of rows, large number of columns of predictor variables. And we do need to worry about tuning to find the optimal performance. All right, so bootstrapping and the random subsets in random forest are what makes it a random forest. And so we're bootstrapping the observations, so we're sampling with replacement the rows of our data, but we're only taking a subset of our predictor variables when we do this. And this is what induces variability among our different trees. And so, bootstrapping, this does a really good job of giving us diversity among the trees. By averaging, I'm reducing the variance, and we also get an out of bag estimate for any statistic I could possibly want off of this. Now, the random subset of the predictor variables, typically I see it either like 0.7 or square root of the number of predictors. This gives us, diversity among our different trees, so they look different, they perform different. This helps reduce overfitting. Remember, the more predictor variables I have, the more prone to overfitting I am. And by reducing the number of predictor variables, this is improving the computation time of how long it's going to take. This can speed things up. Also, by mixing it up this way, I can take feature importance. So for example, we could take the number of times that a variable is used in a split to say, hey, that's how important the predictor variable is. I now have a measurement of which variables are more important or less important. Now, ensemble models make predictions with multiple models. That's true for all ensembles. So an ensemble model is where I take multiple models and put them together in some way, shape, or form. Typically, when we do this, it's going to be either a forest, either something like stochastic gradient boosting, or it's going to be random forest. But potentially, we could do this with any model structure we wanted. But we're going to focus on trees for now. Now, for regression problems, we're going to either do it an average straight or possibly a weighted average if I'm going to weight my observations, or sorry, if I'm going to weight my rows. No, I'm going to weight my trees. I want to weight my trees. And sometimes we'll use meta models, but I typically don't do that. For classification problems, we can have majority voting. We could also have weighted voting if I needed to like tinker with how the trees give information on the overall model. Also, something that's nice about this is that in this classification scheme, I can count the number of times that a level is like voted for, and that can result in a probability of a modeled probability of how likely I would be to see the particular target variable value given the predictor variable values. So why do ensembles even work? Well, first of all, they've got diversity going on. We reduce the overfitting because we average it out. By averaging out the overfitting, I can actually get a better result. We can, we get to reduce some bias out of this, and we get pretty good accuracy overall. Now, variable importance in the Ranger package, we have to actually specify it manually or it won't do it. And so you'll notice that here I've got importance is none. That's the default. That default speeds up the computation time. So if I knew I wasn't going to be using variable importance, like I just needed the best prediction possible, I can go ahead and just not even have it computed to speed up my code. We also have impurity, corrected impurity, or permutation. So what permutation does is that it shuffles a column, it runs a prediction, and it checks to see how much did the accuracy degrade after I shuffled a column. And so here, if I have no variable importance default setting and I try to do variable importance, I'm going to get an error. And I put in a try function to prevent it from like shutting down the entire system. Now here for the impurity measurements, we just use the importance function to pull it out, and we can see which ones are most important to least important. Typically, when I'm going through my feature selection process, I'll trim down to make sure that I have at least a 1 here as the minimum. So if I was going to do feature selection using this particular random forest, I would go ahead and get rid of the basement full bath predictor variable. Here is impurity corrected, and you'll notice that it's similar, but there is a little bit of a difference in the values. And the permutation, you'll notice that this needs to be rescaled to be able to put it on the same footing as the previous two. All right, so remember that feature selection is super important on building my model. If I put in correlated predictor variables or I put in junk predictor variables, it's going to degrade my model. My feature selection step is a critical step in the process. And so variable importance, what that does for me, when I look here, if this is the variable importance I'm going to be using, I'm going to think about, hey, I want to get rid of months sold as a predictor variable, refit the model, then take a look. And then I'm going to look at the weakest one and go, hey, should I get rid of it? Yes or no? Here, I probably would end up getting rid of it. So let's say I get rid of a basement full bath. After I recursively removed these two, I'll rebuild again and I'll consider removing the next one. I'll keep on doing this until I feel like all predictor variables are, are carrying some weight in the model. By doing that feature selection, that will help improve my model performance almost always, not guaranteed. Sometimes if you do like variable clustering and you see a variable is off by itself and then you remove it, it's an anomaly that its information is very different from all other predictor variables. If I remove it, I can lose that information completely. So remember to do your variable clustering. Now, getting rid of variables will improve the interpretability, and also as I get rid of correlated predictor variables, so if two predictor variables are correlated, and I get rid of one, this one's importance is probably going to go up. And so when I do that, it's pretty much guaranteed to go up. It's going to be easier to find out which variables are more important. Thus, I have better interpretability. Also, by getting rid of predictor variables using a variable importance, I'm getting a simpler model. It's less likely to have problems from like predictor variables not being present in the future or being polluted. And so, it's less predictor variables means there's less opportunities for errors to happen when my model goes into production in the future. Now, if I want to do hypothesis testing, the Ranger package gives two methods for doing hypothesis testing, and they're named after the people that that really helped establish these. I'm not going to go too deep into this. Both of these are pretty slick for the purpose of hypothesis testing. For my work, I usually don't worry about this too much. I just go off of the estimated value and trim down the smallest ones until I like the model I've got. But we can get a p-value off of the Ranger package, variable importance, and I can use this to like gain more insight into what's going on with my model. Now, be sure to get rid of correlated predictors. This is true for any model. What will happen if I have correlated predictors and remove one? Let's say I have two correlated predictors and I remove one, that other one is going to shoot up, typically by the amount that the other one had for variable importance. And for predicting with the Ranger package, we have multiple types of predictions. We have response, which is the value that I'm actually trying to predict. And we also have the standard error. So this is the standard error from all of the predictions from all 500 different trees. And also we can have terminal nodes for each of the each individual tree. Amount of output here. I mean, there's a lot here. If we need to trace back particular information, that we could potentially use this to do this. Because sometimes when like, oh, why is it that way? You get it from your stakeholders or your boss. My boss is like that. He always asks like deeper questions, and I just have to dig in, go find it, tell them, and then rock on, move on to the next project. There's also quantile predictions, but we have to do quantile regression and by putting quant reg equals to true and keep mbag equal to true. I've never used it professionally, so I'm not going to talk about it. All right, random forest. These are by far my favorite, most used modeling technique I have for supervised learning. Hands down, this is my go-to. I strongly recommend that you use this. If you don't know what you're doing, go for it. It also has the additional benefit that if I need to get through my data prep stage faster, trees don't don't improve or degrade from monotonic transformations. Therefore, what I can do is I can skip numeric data, you data prep to a large extent when I use decision trees and when I use random forests. And so I really like this technique. This is powerful. This is awesome. And well, that's all I've got for you. Life is short. Do math.